Today we are looking at section 7.5, which is the logistic model. I think of it as the exponential growth model on kind of steroids. Students will analyze logistic differential equations and logistic functions. So my first question for us is, can a population continue to grow at a rate proportional to its size forever? And so that big word here is forever. Well, think about it. We have those population examples with rabbits, the population goes up. With bacteria, the population goes up. All of these things where the population goes up. But in truth, at some point you run out of resources. You run out of space for the rabbits, you run out of food, there's illness, there's disease, there's something. We always have this thing called a carrying capacity, which says, okay, things can continue to grow to a certain point and then they stop. So that's where our logistic growth equation comes in. It's kind of a cool picture. Here, our logistic. So you'll see the first part is exponential growth, and then it flips over to exponential decay. So while we use exponential growth for a lot of things, in real life, the carrying capacity with that logistic growth is probably more realistic. So I like this picture because it describes both pieces. As time goes on, your population size continues to increase. The growth rate continues to accelerate forever and ever and ever. In my second example with logistic growth, as time goes on, growth accelerates quickly. Things are good, there's plenty of food, there's plenty of space, and then all of a sudden we start to run out of space, we run out of food. And so my growth goes to zero, and that's our carrying capacity. So we model that with the logistic differential equation. For a population P that follows a logistic model over time is given by dp dt is equal to Kp times the quantity 1 minus P over M. K is the maximum population growth, M is the carrying capacity, and P is that given population. So this is a more complex version of exponential growth. An alternate form of the logistic equation for population P looks like this one. And what happened in this case, if you factor out an M, if you factor out this 1 over M, you can have the Kp with the M in the front, or the 1 and the M switch spots. So depending on what problem you're given, you might have to pull the P or the M or the K from a different location. So what does this look like? Analyze each logistic differential equation. So we want to know what pieces are what. So in the first example, maybe I can show both of them here. The first example in number 1 is letter A. Letter A has 2 things in the front. I have a 1 minus a fraction. So it definitely looks more like that first logistic model equation. I'm going to write up here. So I'm looking for a K, I'm looking for the P, I'm looking for the M. M's pretty easy. It's the value on the bottom of the fraction, so M is 360. P is here and here, so P remains P in this case. And then K is the value that's with the P in the front, so that's the 0.2. So that's how we pull the pieces of information out. The second equation, part B, has this fraction in the front this time. So this will be the second equation. In this one, again, we want to know what K is, we want to know what P is, and we want to know what M is. So if I look, M is right here, it's 500. P is still P. You know what? I'm missing a piece on this one. This should have a P here. That's a typo on my part. Now, here's what's a little bit tricky about this one, and that's finding the K. So the K over M, P is what's equal to 1 over 5,000 P in this case. So you have to do a little bit of solving. I know that P and P can divide out of both sides. I can do a little bit of multiplying here and say that 5,000 K is equal to my M, but I know that M is 500, right? So 5,000 K equals 500. Divide both sides by 5,000. And I have 5 over 50 becomes 1 over 10. So in this case, K is 1/10. Sometimes they'll give you decimals. Sometimes you get fractions. So if you're looking for a fraction, just be aware that sometimes you can write that decimal as a fraction as well. So instead of talking about the logistic differential equation, here we have the solution to the logistic differential equation, which would be the logistic function. And if you look, our population is going to be m over 1 plus a e to the negative kt. So I know that this looks like a formula that got pulled out of thin air. Truthfully, you could take either one of these, separate the variables, and integrate. There are a couple funny rules that happen in there. I think partial fraction decomposition has to happen if I remember. But just like the other day, we said that y equals just like the other day, we said that dy dt is equal to ky, and then we could just jump right to y equals y sub 0 e to the kt. Just like we can make that conclusion for this problem for the logistic equation function, this is our solution. So once you know it fits one of these first two forms, you can jump right to this formula. You don't have to separate the variables. You don't have to solve for it. So P is the population at time t, M is the carrying capacity, K is the maximum population growth rate, and P sub 0 equals, or P naught equals P of 0. So that's the initial population. And A is equal to M minus P0 over P0. So figure 9 shows the graphs of P equals P of T for a growth model where K is positive and where K is negative. So where we're increasing, K is positive, that makes sense, and decreasing, K is negative. That makes sense when you look at them. Here's a nice one that explains all the different pieces for us. Your carrying capacity. I want you to leave a note here. This is often, or I've seen it referred to as the limit, as time approaches infinity, of P of T. So the limit as we go to infinity, as this goes all the way to the right, I know levels out at the carrying capacity. So that's another way that they ask about carrying capacity. Your initial population is here where you cross the y-axis. The point of maximum growth, and this is important, I've seen this asked as well, this happens at 50% of the carrying capacity. That's where it's steepest. So that's where you have the greatest slope. Your slope starts kind of slow, starts to increase, increase, increase. Here's your max, and then it starts to decrease again. All right, so example 2, we want to identify these different pieces. We want the carrying capacity, the maximum population growth, the initial population, and the population when it is growing most rapidly. So let's start with A, the carrying capacity. So if I look at this equation, and I look up above, I know it used some different letters. Ours used an M in the numerator instead of a C. But this is our carrying capacity. So it's the maximum value at the top. So for letter A, our carrying capacity is equal to 650. Now, they didn't give me any units or anything, so you can just call it 650, that's fine. The maximum population growth, K, so we're going to come up here. Remember, K is the exponent on the E. So the exponent on the E is negative point, hold on. Negative is part of the formula. So I want the positive version in this case. So for this problem, it will be 0.36 is equal to K. For letter C, your initial population, let me come up here, My initial population is at the beginning. So I think what we do, I thought we could just tell right away, but we can't. So P of 0, or P sub 0, would be 650 over 1 plus 24 e to the negative 0.03, whoops, 0.36 times 0. So when we have this, we still have 650 in the numerator, 1 plus, here's my 24, e to the 0 power is just 1. So this is 650 divided by 25. That's pretty convenient. 24, 25, 26. $654 times 6, 24, 25, 26. Yeah, I'm pretty sure about that. All right, good. And then letter D, the population when it's growing most rapidly. So most rapidly occurs at 50% of the carrying capacity. So if I know my carrying capacity is 650, half of that is going to be 325. All right. There we go. That's example 2. They're not too bad as long as you can keep track of which numbers represent what. And I know I stumbled over that a little bit, so that just takes some practice. Last example here. In an experiment involving the spread of disease, one infected mouse is placed in a group of 99 healthy mice. The rate of change of the number of infected mice with respect to t in days follows a logistic model. If P, this is part A, if P is the number of infected mice and the maximum daily growth rate of the disease is 10%, write the differential equation that models the experiment. So here's a key for us. Up here, it says it follows a logistic model. So it's not an exponential model like we had earlier. This one's logistic. So for part A, we know that the population is 100. We know at t equals 0, 1 mouse is infected. The maximum population growth is 10%. So we'll write that as a decimal. And we need the differential equation. So I'm going to use dp dt is equal to kp 1 minus p over n. I wrote my population up here. So I goofed on this one, but it's a good mistake to have. This is actually your carrying capacity. We know that we only have 100 mice, whatever we do. We're never going to go over that. So what we're measuring is the number of infected mice. So that's what we want to find. So when I fill in the values, dp dt is 0.10 p 1 minus p over 100. Okay. For part B, write the logistic function that satisfies the differential equations. We don't have to go through and we don't have to integrate both sides. Remember, we just need that solution. Thought I could reference it quickly, but we'll do it like this. So P of t is equal to m over 1 plus a e to the negative kt. We have the values from up above. We know that m is equal to 100. We know that k is equal to 0.10. And we need to know what this a value is. So from the earlier pages, a was m minus that initial count. So I know my carrying capacity is 100 minus 1 over 1. So this would be 99. If we fill in the pieces, 100 over 1 plus 99 e the negative 0.10 t. So that's our logistic function. And we know it's a function because we're not using dp dt, we're using just plain p. Letter C. Find the time it takes for 1/2 of the population to become infected. So this is the part that feels like exponential growth to me. If I know that 1/2 of the population is infected, that would be p equals 50. So I'm going to say that 50 is equal to 100. 1 plus 99 e to the negative 0.10 t. And so now we have to solve for t. This is where we have to get a little bit creative with our log rules. I'm going to multiply both sides by this huge quantity and divide by 50. So I have 100 over 50 is equal to 1 plus 99 e to the negative 0.10 t. I know 100 over 50 is 2. I'm going to subtract the 1 from the left. So 99 e to the negative 0.10 t. When I divide, I've got 1 over 99 e to the negative 0.10 t. We need those natural logs. So natural log of e to the negative 0.10 t is equal to natural log of 1 over 99. Negative 0.10 t equals, I'm going to simplify this a little bit. I'm going to call it natural log of 1 minus natural log of 99. This is 0. So t is equal to natural log of 99 negative over negative 0.10. Cancel my negatives. Natural log of 99 over 0.10. And I know that's not so helpful, so a decimal number would probably be better. And we get 45.951. And this one is given in days. So it would take 45 days, 46 days. All right, last part. D, how long does it take for 80% of the population to become infected? So this is very, very similar to letter C. But this time, instead of half the population, we use 80% of the population. Equal to the same logistic function. And we go through the same steps. So after all that crazy math, I wind up with 59.814 days, which would really be about 60 days it takes for 80% of the population to be infected. We talk about real life examples, and exponential growth models and logistic models were being used very, very heavily just a couple of years ago when people were tracking the COVID-19 infections and the rate at which the disease was spreading. So it wasn't consistent for the whole path of COVID, but there were parts of it where it was exponential growth for sure. And then things like masking came in, or vaccines came in, or whatever it would be, and it would level out a little bit, and then it would have more exponential growth. So these things really are used to study real life examples. There you go. That's it for Unit 7. Try the independent practice that goes with this, and let me know if you have any questions.